Okay, our next presentation in this session is coming from one of our OG CAMLIS members. So I believe this is going to be David's third CAMLIS presentation. So we'll be hearing from David Krisiloff. He's a data scientist at Google Cloud, and he's going to be presenting structure and semantics-aware malware classification with vision transformers.
Thanks, Lauren. There you go. All right, like Lauren said, my name is David Krisiloff. I'm a data scientist at Google Cloud, and today we're talking about an application of vision transformers to malware detection. Today's talk is going to start with a quick introduction to the subject area. I know some of us in the room have been talking about this for like 5 or 6 years. For others, it may be brand new. We're going to then start with a negative result. We don't talk about these a lot, but this particular one kind of motivates our central hypothesis. And then we'll talk through some experiments to test that hypothesis out and some final results. So we're going to do malware-based static malware detection. Oh, malware-based. ML-based. I do this all the time. ML-based malware detection. So it's static in the sense that we are going to scan a file. We aren't going to emulate or run it in a sandbox, but those are good things to do if you have them available. We're going to look at just the benign versus malicious classification problem today. Yes, there are many other good ML problems in that space to tackle, but that's where we're focusing today. And it's just going to be Windows PE files. My group historically has focused a lot on that. I think the high-level learnings today are applicable to other file types, but all our data sets are going to be Windows executables and libraries. These kinds of models fall into 2 large categories. I'm going to call one the standard machine learning approach, and the other the deep learning approach. In the standard machine learning approach, we have expert-based features. We feed these into a binary classifier. Often it's a random forest, a gradient-boosted tree, sometimes a deep neural net. But all of these models learn directly from the features and not from the actual raw binary file. These are all highly performant. If you look at the open data sets out there, a standard machine learning model is state-of-the-art on all of them. The alternative that we've been talking about CAMLIS for a number of years, and many of the authors cited below are here in the audience today. Look at the raw binary file. We're going to do representation learning. I want the model to figure out what features it needs to classify it correctly all on its own. The typical models in this space are often the malconf models, version 1 and 2. We have our own deep internal CNN, we call the old Mandiant CNN. These are generally a little less performant. Not a lot, but a little. The unfortunate thing is that the expert-based features, which make that standard machine learning approach so good, are really expensive. You need to talk to malware reverse engineers, the people who know what makes malware tick. There are not that many of them out there. It requires a lot of training, and they're in really high demand. So we'd love the representation learning stuff to work just as well, but we're not quite there yet. Though there's a little red asterisk, because by the end of today's talk, we're going to revise that statement. All right, so we're going to start with a negative result. Back in 2022, I went to my boss's boss, and said, why don't we try a vision transformer? They came out in 2021. They were hitting all sorts of state-of-the-art benchmarks on vision problems. It seemed like a reasonable thing to try. We had deep convolutions working. If you haven't seen a vision transformer before, it looks a lot like you had a really cool natural language processing architecture, and then you forced a vision thing to make it look like that natural language processing problem. You take an image in the simplest kind of setup, you break it into patches. You then turn that into a one-dimensional sequence of patches going left to right, top to bottom. You embed those patches, and then it looks like a sentence that you've tokenized and embedded, and you just use the transformer. Surprisingly, this works really well. Now, I'm being a little flippant. There's actually some nice theoretical work that justifies why this should work in the first place, but it really does look like you just hacked your vision problem into something else you already solved. So we tried this, but like I said, this is the negative results section of today's talk. It doesn't work badly. It just doesn't work any better than malconf or a deep convolutional neural net, which is unfortunate because it was much bigger and was the new fancy architecture, and it just didn't pay off. But why it didn't pay off was really interesting. We did some error analysis, and it turns out half of the errors we were making all had one very similar common thing. They all had what's referred to as a section size, half of them had a section size of 0. So the Windows PE file, the executable library on Windows, conforms to this data structure, the portable executable or PE file. It's composed of a header and various sections, and it turns out you can define a section that isn't there. It's actually really common. If, say, you have a big binary and you want to compress it, often what happens is I'm going to compress that data, and then at runtime in memory, it needs to go somewhere. So I'll define a section to put it. And we decompress the data into memory, but it doesn't need to exist on disk. So you have this section of size 0. It's very common. There's open source tooling that lets you do this. So this is not a benign or malicious signal, but it is an important contextual one. I have compressed data in the file, and it's important to realize that's going to decompress into machine code at runtime. And it's not like a compressed JPEG file, which would also be compressed data that I probably don't care about for actually determining if this is malware. Which raises a couple questions, but the most important one is, why am I getting this wrong? And we can hypothesize a couple things, but I think the interesting thing is to ask, well, how does my model know that this thing isn't there? Not knowing that something isn't there is actually kind of hard, because it by definition doesn't exist. So it is there because there is the header that lists out all the sections and a couple of bytes that say size 0 on disk and size greater than 0 in memory. But my PE file is tens of thousands, if not millions of bytes. And if you missed a couple up front that tell you this thing is going to be there in memory, then you've missed the entire problem. Which raises an unfortunate philosophical question. Does our classifier need to be able to parse the PE file to correctly classify it? And I'd argue probably not to 100%, but there are a couple of things, and this is a great example of one of them, where you need to understand the details of this data structure in order to correctly understand what's happening, which is really hard. But helps motivate where we're going today, because maybe we should not ask the model to do that. Maybe we should do it. It turns out parsing PE files isn't hard. It is hard, but there are open source libraries that will do it for you. So our central hypothesis is what we call our structure-aware hypothesis. Maybe by representing the PE data structure, emphasis on that structure, we can improve performance without having to use expert features. Going back to kind of our first slide, instead of thinking of the space of models here as two categories, I'm going to encourage you to think of it as a spectrum. On one side, we have models that are given no help. We have our deep learning approaches. We give it the raw file and say, best of luck. On the other side, we have the models where we spoon feed it all the data we think is really important for it to look at. Hopefully there's some middle ground there where we can give it some data in a cheap fashion that makes the problem easier for it to solve. Okay, so the key principles to trying to do this, we're going to try and provide explicit hints to the model about the structure and the semantics of what it's looking at. We'll talk in detail about the network structure in a second, but at a high level, it looks like the vision transformer where I cut up a picture, except we're going to use a file parser to cut up the file into the semantically meaningful pieces. Then we'll produce some sort of embedding of each of those pieces and push it through a vision transformer. The way we do this is going to allow us to vary the complexity of the information we give the model. So we can ask questions like, if I give it more and more information, do I see more and more improvement, or is there a stopping point? And then at all points, we're going to try and keep the actual human expert cost low. I set all this up. I'm not a malware reverse engineer. I've picked up a little bit over my time in this problem space, but I am rather, I know just enough to be dangerous. Please don't ask me to actually reverse engineer malware. Odds are I'm just going to infect my computer. Okay, so we're going to go into detail on how we inject that expert information into the model. We're going to talk first about how we represent the bytes to the model, and then how we represent the structure to the model. We're going to define in both cases 3 settings, a basic, medium, and advanced, which involves just adding a little bit more and a little bit more expert information. The basic byte information is what all the other models are doing, and it works rather well. I have a tensor, I'm going to fill it with zeros, that's my padding character, and then I'll copy the bytes in, +1, so the bytes are represented as 1 to 256. And that works really well for malconf, it works for the MCNN. But when you start parsing, you hit edge cases that are fun. you can define in Windows PE files sections that don't actually exist. You can say, oh, it exists at some random address. And so long as at runtime, you don't start asking about the thing that isn't there, Windows doesn't care. But how do you fill your tensor? We zero fill all our tensors, and then there's nothing to put in it. And if you leave that as it is, the model may have difficulty distinguishing between padding and between there's a missing section. So we'll define a new character, which we just substitute in if there's a giant parsing error or if we have a missing section. And then in the most advanced setting, we do the same thing, but we also consider high entropy regions of the file. These are indications of encrypted data. And I would posit your ML model cannot learn from the actual sequence of encrypted data bytes, because then you broke the encryption and then, you've broken a lot of laws of mathematics. However, contextually, it's important to know the encrypted data is there. So we can find the encrypted bytes, we can replace them with another new integer, which represents there was high entropy data. I really don't want a model trying to backpropagate and learn through what is effectively random noise. Okay, same idea for the structure representation. And here we do talk about the network in detail. For the simplest setting, we parse out the header, and then everything else is lumped together. We create a one-dimensional embedding of each of these things with a feature extractor and push it through a vision transformer and then classify. The vision transformer itself is 16 layers with 8 attention heads each. We'll talk about the internal dimension or how big that embedding is in our first experiment. The feature extractor is interesting. We're going to reuse the MCNN, which looks a little bit like this. If you're super interested in this model, Jeff Johns talked about it at the very first CAMLIS. The actual architecture is not super important. We've played around with other things for this. We've done deep feed-forward networks. We've done vision transformers. So we hierarchically stacked vision transformers feeding into other vision transformers. They work. The deep convolutions just train really quickly compared to horrible stacking of vision transformers. So we're using the MCNN here. The important thing, though, in the diagram is the color coding. The architecture of the feature extractor is the same everywhere. The parameters are not. We learn a specific header feature extractor and a specific here everything else feature extractor. Because the bytes in the header, even though they are numerically equivalent to bytes everywhere else, they're not semantically the same. If I have bytes in a bunch of machine code, that is not equivalent to the bytes in the import table or in some header which does not contain machine code. They mean different things. And so by learning specific feature extractors, we allow the model to express whatever the meaning is of those bytes in that location in the file. For the medium setting, we parse out more things. Each of the sections gets parsed out and has its own representation. The resource section, which is a special section usually containing things like fonts or different language translations, and which probably shouldn't have code in it, but sometimes does, gets its own feature extractor. Anything appended to the end of the file is called the overlay, gets its own feature extractor. And then in the most advanced setting, we just go another level deeper into the data structure and continue parsing things out. The different components in the header. We have a special call out for .NET. If you're in the AV space, .NET is really annoying. It compiles, if you've not seen it before, into an intermediate representation or IR, which means an executable, which came from a .NET program, has a specific section with the intermediate representation in it, and the rest of the file is mostly boilerplate to get that to run, which means there's a very specific section that has all the actual code you care about. And then once again, its bytes doesn't look like, say, x64 machine instructions. So another feature extractor specialized for just that. Okay, so there are a couple questions we can ask with this setup. The first 2 research questions involve just, if I provide more information to the model, if I parse out more, if I improve my byte representation, do I see improved performance? We could also ask, how susceptible are these models to adversarial attacks? We're in an adversarial space, it's kind of important to look at that. And then finally, how much improvement do I see as I increase the data set size? People like using transformers for everything these days. It's not because self-attention is the best model to architecture out there. It's because it parallelizes well across GPUs and I can throw tremendous amounts of data at it. So for the first 3 research questions, we're going to look at Ember 2018, which is a data set of about 1 million files. For the last question, we're going to look at Sorel 20 million and one of our own internal production data sets. All right. The first result looks at the byte representation and dimension. There's a lot going on this slide. Let's start first with just the leftmost panel. In blue, red, and green, we have the basic, medium, and advanced byte representation. We're looking at test set AUROCs on Ember. The horizontal lines show you various other models that we've benchmarked against, the Malcoms, our MCNN, and at the very top, LightGBM here is the standard machine learning model with Ember features. The middle and rightmost panels are just increasing the internal dimension of the space. That is how much information or parameters are associated with the representation for the header and the sections. You can see here that increasing the dimension of the space helps, but the actual byte representation, not so much. This is more of a negative result. In the lower dimensional spaces, maybe there's a case for increasing the complexity of your byte representation, but once you hit 512 dimensions, it doesn't seem to be doing anything. So going forward, we're going to stick to 512, but we are going to stay with the basic byte representation. For the structure representation, we hit our first positive result, which is nice. You can see going from the basic to the medium to the advanced, that is parsing out more and more of the file for the model, improves model performance. We are getting close to the standard ML benchmark. The best advanced run here was an AUROC of 0.995, and the benchmark is 0.996. I haven't really talked about model sizes yet, so it's worth noting. Depending on your point of view, these are either really big or really small. If you're in the large language model space, these are small. If you're in the AV space, these are big. The biggest here is 55.8 million parameters, which is notably much bigger than the size of Ember of 1 million parameters. If anyone's curious, we should talk in the QA session on that. Let's talk adversarial attacks. These are 8 adversarial attacks where we attempt to manipulate a piece of malware without breaking it to evade our classifiers. And we're looking at the advanced structure in blue, the standard machine learning model in red, and Malconf in green. The y-axis is detection rate. As that goes down, more and more things have evaded our classifier. There are a couple of interesting patterns here. In some ways, we look a bit like Malconf and are not quite as good as the standard ML approach. In a couple places, we are a lot closer or more resistant to attack than the standard ML approach. And at the very bottom right is the shift attack. It's the one I'm the most proud of, because that attack just involves shifting the sections over and inserting random or special bytes in between the header and the sections. But the thing is, Windows doesn't care about anything there, and it doesn't affect anything at runtime. And we're immune to that attack because we parse the file and we no longer care about things that literally don't matter. So we've raised the bar here on adversarial attacks just a smidgen. But at the very least, I think this points out the model is doing something qualitatively different than other neural networks we've had before. Let's increase the data set size. Going to Sorel 20 million. There's a small asterisk here. I don't have all 20 million files. I have 19.7 something. There's like a small smidgen I'm missing. If anybody in the audience has the full data set, let's talk. But if you recompute the benchmarks, the numbers don't actually change. They are 0.997 to 0.998 on the test set. The medium structure is 0.998, and the advanced structure vision transformer is 0.999, meaning for the first time we've hit state of the art with a model that did not use expert features, which is kind of awesome. Continuing to increase the dataset size, we turn to one of our internal production datasets. It's 97 million total files, 90 million train, 7 million tests. This took a long time to run. This one training run is 1.5 months on 8 V100s. If anyone in the audience is an expert on increasing like GPU throughput, we should talk, because this is not fun. This is about tied with our expert model. By AUROC in the 4th decimal place, the standard machine learning model wins out. If you break down performance on goodware and malware, which is how we normally talk to our product folks about this, because errors on goodware and errors on malware are weighted very differently in actual AV products. The vision transformer does better on goodware. The expert feature model does better on malware. I'm going to call this a tie. We are really, really close, and depending on your point of view, one might be better than the other. So to conclude, I'm going to badly paraphrase Einstein. A model should be as complex as it needs to be to fully describe this problem, but no more complicated than that. I think at the very least today we demonstrated your classifier doesn't need to do the parsing. You should just parse the thing for it because it's easy and it's straightforward, and model performance improves tremendously. We've hit state-of-the-art on Sorel for the first time with a neural network looking at the raw file, no expert features. The day when deep neural networks routinely beat handwritten feature classifiers is a lot closer than you might think. And thank you.
Great, thanks, David. Great talk. I see we have a number of questions.
Yeah, hi. Question. So you talked about model size. What if you increase the boosted tree model size? What happens then?
Ooh, that is a great question. Presumably, it would get better. I can say based on our internal production model, we kept increasing the number of trees in that model until our production folks said, you don't get any more RAM on the endpoint. So I would imagine that we can get into a big competitive race here. And there are arguments back and forth. I think the biggest argument for this type of approach is I don't need the expert-based features anymore. I don't need to go, every year or two to my malware reverse engineers going, hey, what's new? I need to encode that in the model to deal with the latest pieces of malware. On the other hand, what I had not talked about is how fast these things go. They're pretty fast. If you have a GPU to do inference, I want to require that everyone who owns my endpoint has a GPU. Probably not. I mean, maybe. Certainly, I think some of the folks who are doing neural compute on everything do. So I don't know. I hear your argument there in terms of yeah, we could get into an arms race on whose model is bigger and doing better. But I think at the end of the day, probably practical concerns on deployment wins out over actual model size. I mean, it depends on your point of view, yes.
Hey, great talk. I was curious if instead of having the separate feature extractors, because I was adding a lot of parameters, could you bake in the structure of the PE in the position encoding? Is that something that you guys thought about or messed with?
It's a good question. I have not tried that. It might be worth trying. My suspicion is it's not going to help. I mean, it might help, but the problem is the position of things in the file can vary. You're not guaranteed that, say, a section containing data or a section containing machine code that executes are always going to happen in the same place or in the same order. And so, I don't know, we have to get really clever with precisely what that positional encoding looks like and maybe try and normalize.
I more mean, let's say you have your traditional position encoding, whatever you were using there, but then adding another vector, or just adding to the position encoding, here's a learned representation of what a PE header is. This is a learned representation of what a section is.
It'd be worth trying, for sure.
Hey, great research. I have a clarification. So I'm assuming you're using heat maps for detection, and you're encountering loss of language nuances through feature extraction layer. Is that what you're doing?
What do you mean by heat map?
Like in the vision transformers, how are you detecting that it's a malware file or a benign file? You're using either heat maps or sequencing, right?
Oh, it's all a one-dimensional sequence. As far as the model is concerned, it is seeing a one-dimensional sequence of the bytes in all the section or all the header. It's not looking at, say, I know there are models out there that will literally turn the malware or whatever file into an image before applying an image model. No. We are a one-dimensional sequence of input bytes.
Okay.
David, I was curious real quick in between questions, the size of the context window that you're giving the transformer, did you experiment with that?
No, but call it clever or call it being very fortunate. I can't go back. If you look at the architecture, there's a tremendous amount of data going in. What's going into, it's going back. what's going into the vision transformer is extremely short. Like once you parse out, like there are like maybe a dozen sections in the header, which means I have 13 tokens that go into the vision transformer. You don't need a large context window, which is convenient.
Well, I guess I was wondering, yeah, before you did the like parsing, like.
Yeah. It doesn't matter so much for the deep convolution, but if, per se, the feature extractor was another vision transformer, because we had tried this, you do need to be really careful and clever with how big all the inputs are going into it, because it has a context window size. So I need a blackboard to draw it out. But basically, yeah, there are sometimes issues in that first layer if you use a vision transformer. And we can talk more afterwards if you're curious.
I'm going to yes and a couple of the questions. Since you're using a parser, you're getting a syntax tree. And since you're using a vision transformer, you can reason over images. And my understanding is that there's these gizmos called tree maps that Ben Schneiderman at Maryland did a zillion years ago, where you can represent a tree as a, as an image. And I can imagine you pack feature vectors in for the attributes of the nodes in the tree. Have you considered reasoning over a representation like that?
No and yes. So in this specific instance, we don't have the abstract syntax tree. We're not at any point decompiling the code and getting the original source code. So when we parse the file, I'm talking about parsing it into the kind of component blocks of the PE file, not an abstract syntax tree. However, yeah, maybe. I was going to say for source code files, we have other models we played with where we do parse it and get an abstract syntax tree. And then, yes, that is a useful representation to learn classifiers over. And yeah, that's fair. I mean, the PE specific case, like the resource is totally a giant nasty tree structure. Sections themselves, maybe, maybe not. But it's worth thinking about. I have to think about it some more.
Okay, thank you. Oh, one more question. Okay, we'll let it ask the question.
I have lots of questions. I'll restrict myself to what I think is maybe the most general question. Sorrel was released with like the models so that people could sort of play with the results even if they don't have 97 million files to train on. Any chance that you're going to be able to release some of these models for people to train on or to play with as maybe pre-trained models to then support other activities?
It's a good question. I will ask my legal folks and let you know. I honestly don't know the answer. But Google does release models, so it's not necessarily a no.
Cool. Thanks.
All right. Thanks, David.